Okay. There we go. Okay, my audio is all fine. That's good. Right. Yeah, apologies I was slightly late. As everyone knows, caffeine is a requirement for doing physics, so I had to go and make tea. Noise. So, the first thing I want to look at is this kind of way of writing electromagnetism in a covariant way that I think Machu asked about last time, but I think it needs a little more talking about. Okay. Give me 1 second. I just want to get my screen set up, because also after that I will definitely want to look through some physics memes. So I just want to get that set up too. Okay. Cool. That's all right now. Okay, yeah. So, I guess the place we should start is just Maxwell's equations. Because what we're trying to do is we're trying to find a covariant way of writing Maxwell's equations. So a way that involves tensors that transform in, the nice covariant way we know tensors should transform in special relativity. So first let's write down all of Maxwell's equations. That's Gauss's law, the divergence of the electric field is the charge density, the divergence of the magnetic field is always 0, assuming no magnetic monopoles, which is a pretty safe assumption. And then the curl of the electric field is minus dB by dt, and lastly the curl of the magnetic field is mu naught epsilon naught dE by dt plus mu naught J, where J is the current density. Okay, so the nicest way to do this, or kind of the thing we want to do next, is to introduce potentials. So interestingly, in electromagnetism, the potentials are really the more fundamental thing than the fields. I think the nicest way you can see this, or the nicest evidence of this, is this so-called, I never know how to say the name, but I think it's the Aronov-Bohm experiment. So this is a kind of quantum mechanics experiment that talks about how the presence of a magnetic field influences what happens to an electron, when you make some measurement of it in some way. I can't remember the exact setup, but the point is that you can do this setup so that you produce a region where there's no magnetic field, but by continuity of your potential, you still have a vector potential, the potential that gives rise to the magnetic field. So you would expect that if there was no magnetic field, you would see no observable change in the behavior of the electron, or in how the results you get from measuring something about the electron. But actually the presence just of the magnetic potential, never mind the magnetic field, actually changes this. So the magnetic potential, or the vector potential as we call it, has an observable effect on things, even when there's no magnetic field. So we take that to mean that the potentials are the more fundamental thing than the fields themselves. Something related to capacitors. I'm not sure, it's a setup where I think you have like cylinders of conductors and you have some current, and you can produce a region. If you have like these two concentric conductors, you can produce a region where there's no magnetic field, but there will still be a vector potential. and within this region there'll be some observable effect on the electrons in there. And if you know about quantum mechanics involving electric and magnetic fields, it's actually the vector potential is the thing that couples to the charge, not the field itself. When you try to include at a sort of semi-classical level the effect of electric and magnetic fields in like Schrodinger's equation or something, it's the potential, the vector potential, that couples to the charge, not the magnetic field itself. So we want to write these things down as potentials, or this is an indication that writing things in potentials is an important thing to do, because these potentials seem to be more fundamental than the actual fields, than the B and E fields. So from this Maxwell's law, the divergence of B being 0, from a sort of standard vector calculus identity, it's convenient for us to define this vector potential A such that B is given by the curl of A, because this is identically 0. If you take the divergence of the curl of something, it's always 0. So this will always satisfy this equation here. Then if we look at equation 3, that the curl of E is equal to minus dB by dt, that gives us that the curl of E is equal to minus the curl of dA by dt, just by putting in this potential equation we had for B, and you can arrange that to be the curl of E plus dA by dt is equal to 0. Okay? And the curl of something being 0 means that you can define it as the gradient of some scalar function. This is another fact about from vector calculus, that if you have, you know, the curl of the gradient of some field, that is identically 0. So now we define a new potential phi. So we define the thing that is inside of the curl, which is this E plus dA by dt, to be minus the grad of some scalar field phi, which it will turn out physically will be the electromagnetic potential. So we've now got an equation for the electric field in terms of these two potentials, the scalar and the vector potential, and we also had from above, remember, an equation for the magnetic field in terms of the vector potential. Okay. And now, as motivation for how we'll define these covariant quantities related to the electric and magnetic field, I want to try and derive a wave equation for these potentials. Okay. So far, this has come from the third Maxwell equation. Hello to IMD. That's kind of you to say. And this one has come from the first Maxwell equation. That is 1 being the divergence of the electric field and 3 being the curl of the electric field. Okay. And what we can do now is we can plug these equivalent forms for the magnetic field and the electric field back into these Maxwell equations that we got them from. Okay, so we can plug this back into wait, now which one is it? Curl of that one looks like this. So if we put curl of A back in here where B is, and we put this whole funny expression for E in here, you end up with the double curl of A, which there's a convenient identity for we'll look at in a minute, is equal to minus mu naught epsilon naught and then we've got a derivative with respect to time of grad of phi plus dA dt, where I've taken this minus from here outside of both of them, okay? And that's still plus mu naught j. So we can play around with this some more. This has a convenient vector calculus identity with which we can simplify it. If you take the double curl of a vector field, that ends up giving you minus the Laplacian of the vector field plus the grad of the divergence of the vector field. Okay, I'm kind of rushing through some of this vector calculus stuff a bit to get to the tensory stuff, but I hope if you're following this, I hope you kind of know some of this vector calculus stuff, and it's all right. Okay. So that gives us on the left-hand side this equation here, and then on the right-hand side, still the same thing as before, but now I'm going to kind of move this time derivative through. I can commute the time derivative with this grad here. So I can rewrite this as minus mu naught epsilon naught grad of d phi by dt minus mu naught epsilon naught second derivative with respect to time of a, and still plus the mu naught j. Okay. So I've got two terms that both have a grad outside of the front, and I want to bring those together. And what I also want to do is I want to bring this Laplacian of a over here onto the right-hand side, so it can join up and be together with the time derivative. So I'm going to do some juggling, and that gives me minus mu naught epsilon naught time derivative. Oh, this is a vector. This should be underlined. Second time derivative of a plus Laplacian of a, and now I've got this grad term. So this term here, but I'm also moving this term over to join it. So that is grad of d phi dt plus divergence of a, and now I'm going to move the mu naught j term over to the other side. So now this becomes equal to minus mu naught j. I don't think I've made any slip-ups there, but I may have done. This all looks okay anyway. So this term here, I'm not going to show it, but we're actually free to set this term to 0. Okay. And if you wanted to show that you were free to set this to 0, the fact that you're free to set it to 0, rather, comes from this gauge freedom you have in electromagnetism. So although I've written down that my potential A and phi are defined like this, I'm actually free to add on extra terms to A and phi, as long as I do this in such a way that it doesn't affect the E and the B fields. The E and the B fields are kind of the things we measure in electromagnetism. So as long as I can transform these potentials in such a way that it doesn't change the E and the B fields, that's okay. And if you can show that with this freedom that you're allowed to do such that you don't change the E and B fields, you're allowed to set this quantity here, d phi dt plus divergence of A equal to 0. Okay. So I'm setting this quantity to 0. I don't have to set it to 0. It's a freedom to set it to 0 by this gauge invariance, but it doesn't necessarily have to be 0. Okay. Oh, actually, have I made an error here? I think I have made an error. There's no mu naught epsilon naught here, so actually there should be a 1 over mu naught epsilon naught here, because I've brought them inside the bracket. So there should be a 1 over epsilon naught mu naught there. Now, have I made any errors? Should that be a minus sign? Let me double check. Where did I put it in? I put it in. Okay. No, it looks okay. I think. Yeah. All right. But this should have a 1 over epsilon naught mu naught here. Okay. And for convenience, because I'll use it quite a bit later, I'm going to remind you that c squared is equal to 1 over epsilon naught mu naught. Well, yeah, I mean, technically, I should probably just set c equal to 1. That would be convenient, because then it would get rid of this epsilon naught mu naught. But I want to do it... I don't want to set c to 1 right now, because I want to write it so that it's recognizable as electromagnetism. And typically, when you write down things in electromagnetism, setting c to 1 is not so helpful in normal, non-covariant electromagnetism, because you don't always have these combinations of epsilon and mu. You often just have one of them on their own, which you can't independently set to 1. Okay, so I'm going to rewrite this. Well, actually, what I'm going to do is I'm going to times this whole thing by epsilon mu naught. So I'm going to have epsilon naught mu naught and get rid of this instead, because this is actually a little nicer. Okay, so I'm writing this as 1 over c squared d phi dt plus div of a is 0. This is my gauge condition, and this is often called the Lorentz gauge. Not the Lorentz with a T gauge. Lorenz and Lorentz, different people. I think often people accidentally call the Lorentz gauge the Lorentz gauge. I mean, I definitely always do. In fact, I may have got it the wrong way around. It might actually be Lorentz. I'm pretty sure it's Lorenz, though. But anyway. So if you set this to 0, which you can do with your gauge freedom, you get a nice equation for A, just involving these 3 parts here. And that equation, and also I'm going to again replace the mu naught epsilon naught by c squared, or 1 over c squared in this case. You end up with 1 over c squared, second time derivative, plus Laplacian squared, well, I don't need the brackets, is equal to minus mu naught j. Okay, assuming the gauge condition that we have here, the Lorentz gauge, which you're free to choose, but you're also free not to choose. Sometimes you will choose just a set divergence of A is equal to 0. This is called the Coulomb gauge, and it's usually what you would use in electrostatic problems and things like that, because then it means your potential is your electric potential, your scalar potential is not changing. Okay. So this is one equation. This is the wave equation for the vector potential. And now I'd like to get a similar equation for the scalar potential for phi. So the way I do that is I'm going to use, where is it? Equation 1, that the divergence of E is rho over epsilon naught, and I'm also going to have to use the gauge condition. So writing E as the expression in terms of potentials we have, equation 1 just becomes divergence of minus grad of phi minus dA dt is equal to rho over epsilon naught. Okay, and divergence of grad, this is how we define the Laplacian. And then we've got minus, and again I'm going to commute the derivatives. I'm going to commute the divergence with the time derivative, so I'll rewrite this as d by dt of divergence of A. And that's equal to rho over epsilon naught. Okay. And now what I can do is, from my gauge condition, I can rewrite divergence of A in terms of this time derivative, because I have this combination of divergence of A plus the time derivative is 0. So that means divergence of A will be minus this whole thing here. Okay, minus 1 over c squared d phi by dt. Which means this equation becomes, the minuses will cancel, and I have d by dt of 1 over c squared d phi by dt, and that's equal to rho over epsilon naught. Now I'm going to rewrite this again slightly so that I have a +1 in front of the Laplacian and a -1 in front of the time derivative, which is just because I've chosen my metric to have a certain signature. I want to write it like that. And also I want to compare it with the equivalent wave equation I found for the vector potential. So now if I've multiplied the whole thing by -1, this turns into a minus rho over epsilon naught. Okay. So we've noticed something interesting. Right, we should have noticed something interesting by now. And that is that these two equations for the electric and the vector potential are actually pretty similar. They have the same form involving this Laplacian and second time derivative, and they're both proportional to some kind of density terms. You've got a charge density for the scalar potential and a current density for the vector potential. So this sort of motivates that we might be able to combine both of these equations into one equation. If we what we can do is we can sort of separate out the left-hand side here into an operator that looks like this, which is just an instruction to take the second derivative of whatever you multiply by on the left, and then another instruction to take the Laplacian. We can rewrite both of these as this operator here, multiplied by, well, in the case of phi, it's multiplied by phi, or acting on phi rather, to give this. And in the case of A, it would be exactly the same, except now we'd have an A here, and a minus mu naught J here. Okay. So we've written it in terms of the same operator on the left-hand side. And this operator, sometimes people write it as box squared, or sometimes they just write it as box. Personally, I don't really like that convention. In special relativity, I will usually write it in this way, as d mu times d mu. Okay, but technically this is a little bit naughty doing this so early. I'm using tensor notation, which is okay for this operator, because this operator will transform as a Lorentz scalar, or in this case as, you know, a contraction of a covariant and a contravariant tensor. But what I don't know is about phi and about A. These things I expect won't transform as Lorentz vectors or as Lorentz scalars. So phi is a scalar and rho is a scalar, but these things are not Lorentz scalars, meaning if I do a Lorentz transformation on this system, phi does not stay as phi and rho does not stay as rho. And likewise, but perhaps even more obviously for A, because A is a 3D vector, not a 4D vector. If I do a Lorentz transformation on J, another 3D vector, or on A, a 3D vector, I won't get the same sort of form that I did before. This idea that when you transform the quantities in your equations by a Lorentz transformation, that you should end up with the same form of equation you had before, is really central to special relativity. Okay, it comes from the fact that there is no preferred coordinate system. All inertial observers without acceleration, are equivalent, and we shouldn't prefer any one of them to any other. So if the quantities in your equation in special relativity appear to have a preferred coordinate system, then they're not what we would call covariant. They don't respect the symmetry of special relativity. So it's not good that phi and A appear to change form when we change reference frame. So what we have to do, this is me, yes. Oh, you found the emote. Yeah, I thought it was quite funny. So what we have to do now in order to fix this is we have to find quantities that do transform in the right way, according to special relativity. Okay, so these should be the vectors, they should be 4D vectors, instead of 3D vectors, so something like A and J are no good, these are 3D. So we need some 4D vector that will transform in the right way and will include both of these equations. Okay. Now this is kind of a fudge, because what I'm going to do... No, it's okay. You're allowed to post the emotes. It's fine. What we should do is we should prove that these things... I've just noticed the camera's not actually really looking at me. Is that any... Okay, that's slightly more central. What we should do is we should prove that these things transform in the appropriate way. So when I define this new... got it as well. So when I define this new 4 vector, that it will be this 4D version that incorporates the electric scalar potential and the magnetic vector potential, we should prove that it's really covariant. We should prove that when I do a Lorentz transformation on it, I get something of the same form that importantly represents the same physics. But we're not going to do that because it's a bit long, and well, frankly, I don't want to. But, you know, it's just to be aware this is something we should prove. But what I'm going to do is I'm going to state the form of this 4 vector, and I'm going to tell you that it transforms as it should do correctly under Lorentz transformations, okay? And the way we do this typically, motivated by this sort of apparent similarity between rho and by j, and between phi and by a, we define 2 new quantities, okay? 2 new 4 vectors. I define the 4 potential to have a time-like component, or a 0 component, phi over c. And again, this would all be easier if we'd set c equal to 0, but like I mentioned earlier, I don't, because we want to compare this in the end with Maxwell's equations, which typically we don't have c equal to 1 in, because it's not so convenient in those equations. I'm not going to drop the c's right now. So it has a 0 or time-like component phi over c, and then the remaining space-like components, the 1, 2, and 3 components, are this vector potential A. Okay? And likewise, I define the 4 current density. This is this 4 vector version of the charge density and the current density as being rho times c, and then the ordinary electric current density from before. Okay, so these are 2 new important quantities. And like I say, really what I should do is I should prove that these things are 4 vectors. Okay, the fact I've given them this nice label here with a mu, this carries a lot of weight to it, this mu. What this mu means, it means this thing is a 4 vector. If I transform it by a Lorentz transformation, all of its components, or rather, well, no, hang on. What it means is, if I change reference frame, if I go into a new reference frame, the way I find what each of its new components look like is by doing a Lorentz transformation on the entire 4 vector. So this is not necessarily true. I can't just slap, you know, any scalar and 3 vector together and say that it'll be a 4 vector. Okay, so, you know, I couldn't do something like, I don't know, take something weird like temperature, which is a scalar, and acceleration. I couldn't take temperature and acceleration, you know, put temperature up here, put acceleration up here, and say, ah, this is a 4D vector, therefore it's a 4 vector, because its form would not stay the same when I change reference frame. So something being a 4 vector carries a lot of meaning, and at the moment we've not proved this is a 4 vector, but I'm asserting it is. And certainly you can show that it is a 4 vector if you know how electric and magnetic fields transform when you change reference frame, which you can derive. You can show that these potentials here and this current density will transform in the right way. It makes sense that electric and magnetic fields should be sort of linked together by special relativity. So if you think about current and charge, well, imagine you've got current flowing through a wire. If you've got a wire in front of you, you've got current flowing from one end to the other, you know that that produces a magnetic field that wraps around the wire. Well, what if you switch into the reference frame where you're following the charge as it goes down the wire? So now in your reference frame where you're following the current as it goes through the wire, it doesn't appear like there is any current. The charge just appears to be sitting still while you move alongside it. But it's still charged, so you would still expect to measure some kind of electric field. So all the experiments you could think of, which would be able to tell you whether it's a magnetic field, whether it's an electric field, will actually depend on how you're moving with respect to it. So if you tried to do an experiment in the reference frame that you're moving alongside the current, so that it appears just like a stationary charge distribution to you, you would see some observable effect, and someone that was standing outside of the wire, that was just standing still watching the current go through and watching you fly alongside the current, they would watch you doing your experiment and they would see the exact same thing you would see, the same results, except they would interpret what caused the result, whatever it might be. I can't think of an example off the top of my head. They would interpret that as being due to a magnetic field, due to the current. Okay, so it doesn't violate any sort of observable things. Experiments are all still, in agreement with each other in the ways that they should be in special relativity, but the things that are responsible for certain effects will depend on your reference frame, whether it's a magnetic field or an electric field. Okay, so it makes sense that electric field and magnetic fields should mix up in some way. Okay, so what I can do now is I can rewrite observer effect. Yeah, observers are central in special relativity. It's interesting to think about all these ways that you can resolve these paradoxes, although I've not stated a specific example that would appear to be one, but they all are nicely resolved. What I can do now is I can combine these two equations, in fact, all into one equation. And I'm going to do that using this operator I've defined here as being d mu, and these new 4 vectors I've defined here. And again, remember, I've told you these are 4 vectors, I've not proved it, but trust me, they are. So the way I can do that is I'll take my operator in this covariant notation using d mu's. This should multiply, here it will multiply phi, up here it multiplies a. So I'm going to multiply it all by a mu. Well, actually, I'm not going to use mu, I'm going to use a different index nu, because, by these standard techniques in relativity with manipulating tensors, you never can have more than 2 lots of the same index multiplied together. Okay? These 2 indices here are contracted, the 2 mu's, but then this is a separate index with the nu here. Okay? You're skinny in my frame. Oh, I see. Right. I didn't get that for a minute. Yeah. Length contraction. If you're moving very, very quickly, you'll look pretty skinny to someone else. Okay. So that's the left-hand side. Then the right-hand side, now I want to write in terms of this new 4 current density. And you can check that with all of these kind of epsilons hanging around, mu's hanging around, and this c hanging around here, that we do in fact get the right thing. All the factors of c nicely cancel, and it turns out that both of these equations are incorporated into this equation here. Okay, so this is our 4 potential wave equation. Okay, so this equation here results from Maxwell's equations, but it doesn't kind of explicitly tell us Maxwell's equations. If you like, this tells us some particular combination of Maxwell's equations, but it doesn't actually tell us the individual parts of Maxwell's equations. It only tells us, what they can combine to give. So we want to get something a bit better that tells us specifically Maxwell's 4 equations. But now we've got this vector potential. This thing is very important. So the reason I wanted us to do this, to derive this wave equation and to try and translate it into this covariant way, is to sort of motivate why we define this 4 potential here, because the 4 potential plays a really important role in what we'll do next. Okay, so the next thing I'm going to do, I'm kind of going to define it backwards. So I'm going to state the definition of this new quantity, and then I'm going to show that this new quantity gives rise to the right equations. Or rather, I'm going to, well, you'll see what I'm going to do. I'm going to define a new quantity, which I define like this. This is sometimes called, I think, the Maxwell tensor, or the field tensor. I can't remember all the different names for it. But I define this new quantity, and now what I'm going to do is I'm going to work it out explicitly. Well, I mean, I'm going to write it down because it takes a little while to do all of it. Oh, what notebook software am I using? I'm using, oh, what's it called again? Notability. And then I just share my screen while I'm doing it. I do that with all of my teaching and tutoring, and it's pretty good because then you can just save all of it. Or like actually it automatically uploads to my Google Drive as a PDF. It's pretty nice. Faraday tensor. Yeah. Okay. So if you compute this thing, remembering that a mu is defined in this way, and that derivatives like this, upper derivatives, are derivatives like this, derivatives with respect to lower index in the coordinate, and I define my upper index vector to look like this, and therefore with a contraction with the metric, the lower coordinate vector will look like this. So it means actually whenever you do this upper derivative with respect to time, so for example if you do d0, that actually corresponds to minus 1 over c d by dt. This minus sign is different. So if I was instead considering the lower derivative, this would actually be a plus. These are just things to keep track of, because if you wanted to try and derive the explicit form of this tensor, you would have to make sure you were careful with all the signs and stuff like that, okay? But if you follow through with this anyway, what you get is a 4x4, well, if you write it in matrix form, you get a 4x4 matrix that corresponds to this tensor that has a 0 in the first element, then you've got the x, y, and z components of the electric field divided by c. You actually get zeros all along the diagonals, and sort of to save you some time in actually computing this thing, rather than thinking, okay, well, what will this element be, what will this element be, going through all of them, you can look back at the definition of the tensor and notice that it's manifestly antisymmetric. So if I swap mu and nu, I will always get minus what I started out with before. Okay, so mu here is labeling which row I'm looking at. So this I'm going to call mu equals 0, this one will be mu equals 1, and so on. And nu is labeling which column I'm looking at. So this corresponds to the matrix being antisymmetric. And all antisymmetric matrices must have zeros along the diagonal. Okay. And also it means I can now just fill in these elements along the reflection along the diagonal will just be minus whatever the other elements are. So you don't have to compute every single element. You only have to compute 6, and then all of the others will be reflections with a minus sign in front, okay? Because the matrix is antisymmetric. And then you'll find the magnetic field components appear like this. With a 0 here. And then reflected along the diagonal, again, they'll be negative what they are on the other part. So, well, let me space out a little bit, so it's clear which bits are in which column and row. This will be minus bz, this will be by, this will be minus bx. Okay. So that is what our Maxwell tensor, Faraday tensor. Maxwell tensor, Faraday tensor, I can't remember which one it is. That's what our tensor will look like anyway. So now what I want to do is try to rewrite Maxwell's equations using f mu nu. Okay. So let me get back to Maxwell's equations and bring these down again. Okay. So the first equation, the divergence of the electric field is rho over epsilon naught. The way I can write this in terms of the field tensor. Oh, have you downloaded the app already? Yeah, no, I really like it too. It's great. I am using an iPad. Yeah, it's kind of so like there's a tool here where you can circle things and then move them around. And I find now when I write on like normal paper, I will like circle stuff with my pen and then try and drag it. So if you look through any of my handwritten notes, they've got like random circles around them where I circle something I want to move, and then I remember I'm using pen and paper. So it's a total mess. So I tend to try and stick to the iPad now because I also make loads of mistakes whenever I'm doing work. So being able to kind of go back and edit them is really helpful. And I guess it's kind of more environmentally conscious too. Not that that's my particular motivation, because I'm not using. I used to get through lots and lots of paper doing work, but not anymore. So anyway, what I can do is I can rewrite this left-hand side in terms of the field tensor. So let's write down explicitly what this looks like. The divergence is just shorthand for this. Okay. And now what I want to do is I want to go and rewrite these electric field components and this charge density scalar all in terms of components of my covariant quantities. So I want to rewrite in terms of f mu nu, also j mu, and derivatives, things like this, all these covariant things with Lorentz indices, these mu and nu indices. Okay. So what can I do? Well, the x component of the E field, this component here, this corresponds to the 0, 1 element of the field tensor. So remember this row up here, the first number is what corresponds to the row, and the second number is what corresponds to the column. Okay, and I'm counting from 0 down to 1, 2, and 3. You could have gone 1, 2, 3, 4, but generally in relativity people count 0, 1, 2, 3. 0 for the time-like component. Okay, and likewise this y component will be f02, the z component will be f03. Okay, so now I'm taking, instead of doing the derivatives of ex, ey, and ez, I'm doing the derivatives of f01, f02, and f03. Okay. All times by c as well, because remember it's e over c is equal to these components. So now it looks like this. f03. And then the right-hand side, that includes the scalar, what's it called? The charge density. I want to rewrite this in terms of a covariant quantity. So the covariant quantity I'll rewrite that in terms of will be J, or rather a particular component of J. Remember, J is defined in this way. So if I want to rewrite rho in terms of J, I will say that rho is equal to J0 over C. Okay? So that is J0 over C over epsilon naught. Now don't confuse the noughts on the epsilon and the mu naught are not tensory noughts. These are just constants. Okay, epsilon naught is the name of the constant, mu naught is the name of the constant. Okay. So I'm also going to rewrite my derivatives here a little bit. So remember we defined the vector in this way. Such that in this notation, this means that x0 is equal to ct, x1 is equal to x, x2 is equal to y, and x3 is equal to z. Okay, so I'm actually going to rewrite this derivative a little bit. Instead, I'm going to write d by dx as d with a little subscript 1, okay, which just translates to d with respect to x1, or in other words, d with respect to x. And likewise, d2 would be d with respect to x2, or d with respect to y. Okay, hopefully that makes some sense. This is just notation anyway. So now my left-hand side up here, also what I'm going to do is I'm going to divide this whole thing by c. So I'm going to bring this c that appears here and bring it over to this side. Okay. So when I do that and I rewrite using this slightly different notation, this thing looks like this. And I'm dividing by c. So now on the right-hand side, I've got j naught over epsilon naught c squared. Okay. And again, using the fact that c squared is 1 over epsilon naught mu naught, this whole thing becomes, replacing the 1 over c squared with epsilon naught mu naught, this will just leave me with a mu naught up here. Okay. So this is one equation. This is the first Maxwell equation, the divergence of the electric field, written in terms of this Faraday tensor. Okay. So this is one Maxwell equation. Now at the moment, this is written in terms of components of the tensor. So it's not clear in the way this is constructed that it's a covariant formalism that will transform according to Lorentz transformations, because we've written it specifically in terms of components. Okay, so what we'll do next is we'll write another Maxwell equation, and then we'll show that both of these, oh hello non-dairy neutrino, and then we'll show that both of these equations are kind of generalized by a covariant expression. Okay, and again, sort of without proof, we'll assume that, well, actually no, with proof, don't worry, I'll get to it. I'm getting ahead of myself. Okay, let's look at the next equation. So this is what Maxwell's first equation becomes. Okay, the one involving the divergence of the electric field. Now I want to look at which equation? Now I want to look at this equation. I want to look at equation 4. Okay. So now equation 4. But equation 4 is a little annoying in that it's got this curl of B. So I'm not going to look at a general component of equation 4. I'm just going to look at the x component of it, because this is a 3-vector equation. It's a 3D vector equation. So that really means that it's 3 ordinary scalar equations. The left-hand side, you know that what this curl means is to take combinations of the derivative of the different components of B in such a way like dBz dy minus dby dz is the x component of this thing. The y component will look like db x dz. Wait, is that the right way around? It'll be, wait, x, yep, that's right, minus db z dx. That is the y component of this thing here. And then the z component will look like dby dx minus dbx dy. But I'm only going to be interested in one component, and then I'll kind of assume that it's true for the rest of them, because I don't want to complicate this more and get into using epsilon I jk stuff to write down write down vector curls. So I'm just going to look for the x component of this equation. Okay. So that is the x component of the left-hand side. Then the right-hand side is mu naught epsilon naught, the x component of x, d by dt, plus mu naught times the x component of the current density, the 3-vector current density. So now I'm going to do the same thing. I'm going to go up and try and extract these different components, these things here, as components of our nice covariant vectors. Things like f mu nu and j mu. Okay. So bz, I'm going to pick this bz here. This is in the first row of the tensor. Because again, remember, I count this as the 0th row up here. So this is row 1. So it has mu is 1. And it has column of 2. Okay. So this will be given by f12 bz. So that means I will write this as d f12 by dy. Now I need to go and extract by from the tensor. By is given by, well, it's in the first row, so it's f1, and it's in then the third column, so it's f13. But of course, f13 is equal to minus by, so by will be minus f13. Okay. So this is minus derivative with respect to z of minus f13. And then the right-hand side, we've got the mu naught epsilon naught. Now we need to go and extract ex from the tensor. Ex, this is now the first column, 0th row, so that is c times f01. D by dt of c times f01. And then jx, extracting that as a component from here. The x component, well, that's just going to be the first component down here. Okay, so the first component of j, which will be like jx, jy, jz, as the 3-vector, and the first component is just this one here. So I'm just going to call this j1. Okay. Right, now what I'm going to do is I'm going to translate these derivatives into covariant derivatives, well, not into covariant derivatives, that's a different terminology, into derivatives with these covariant indices, or, you know, as in things involving mu's rather than written in terms of tx and y, something as a component of this, okay? But I'm going to do it in terms of these lower vectors. So the first one, d by dy, this is just d2 of f12. Now there's a minus sign here that cancels, so that gives me plus d3 of f13. And then on the right hand side, what I'm going to do is write d0 is equal to 1 over c d by dt. Okay, so that means this d by dt here I replace by c times dd naught, c times d naught, like this. Okay, so this goes to mu naught epsilon naught. Again, remember these naughts here are not indices, they're just labels. C times d naught f01. Okay. All right. And then that is still plus mu naught J1. So what I'm going to do now is I'm going to... why is there a c squared there? Is that all okay? I feel like I've picked up a factor I shouldn't have picked up somewhere. Oh, I feel like I should have... Ah, no, okay. This should be a c squared, because I've got one factor of c coming from the derivative and one c up here from how I've extracted this component, because remember it's E over c is equal to the components of the tensor, so the E field will pick up a factor of c when I multiply it by the tensor component. Okay, so this is a c squared. And then I use the fact that c squared is equal to 1 over epsilon naught mu naught, so this actually cancels these components here. And now I want to bring all of my derivatives to one side. So I'm just going to be lazy and copy these. And then I've got minus this derivative here, and that's equal to mu naught J1. Fade effect? What fade effect? Oh, I just delete the text. Yeah, it's like if you go through and delete it without taking your hand off, it sort of fades it. And then it deletes it when you remove your hand. There's no kind of a spookiness going on there. It's just how it happens to erase things. And now what I'm going to do to turn this into a nicer form is I'm going to use the asymmetry, or rather the antisymmetry, of f mu nu. So I mentioned it earlier, but I don't think I wrote down explicitly that if you swap the indices in f mu nu, you pick up a minus sign, because this thing is manifestly antisymmetric from its definition. Okay, so that means I can rewrite this whole entire thing here as plus, and then swap these two indices up here. And when I do that, I get this expression, where now I'm swapping 1 and 0. And now this is the expression for Maxwell's curl of B equation in terms of these covariant quantities, like the Faraday tensor and the 4 current. Okay, but remember, this is only the x component. So the y component, the z component, they will also be present, but they will look, so this is the x component, the y component, we can also trivially write down, we'll just be swapping, oh, well, how trivial is it actually? What will we do? I will change this to a 1 and a 1, change this to a 2, then swap the other things for 2s. Okay, I mean, you'd have to work through it, but this is what it'll turn out to be anyway, for the y component. So this would tell you the y component of that particular one of Maxwell's equations we were looking at, and you could do the same for the z component. The point is that it contains, fully in component form, this Maxwell equation here. Okay, so we've written this Maxwell equation in this way, as this sort of sum of derivatives of the Faraday tensor, and we've written this Maxwell equation involving the curl of the B field in components will be this equation plus a corresponding one for the y component and another one I've not written down for the z component. Okay, you could write it more compactly, but we're not too worried about that right now, because there's an even more compact way. We'll write it in a second. So let me bring this equation down here that represents the first Maxwell equation. So let me put this one here, and then this other one that represents a component of a different Maxwell equation here. Okay, so remember, this is the div of E1, and this is the curl of B1. So these are different Maxwell equations represented by these two formulae here. But you'll notice that they're actually very similar when you write them in terms of these components of the Faraday tensor and what we defined as the four current density. Okay, and this motivates, you can generalize all of these equations, this equation for the divergence of E, and these three equations that look very similar to this you'll get for the three components of the curl of B. They're all generalized by this following equation. Ooh. Hang on. That's a mu by this equation. Okay. So this equation here, written purely in a covariant form, where everything with an index that has a mu or a nu will transform according to a Lorentz transformation. This is the covariant way of writing equation 1 and equation 4 of Maxwell's equations, which I'll remind you are this one involving the divergence of E, and this is the one involving the curl of B. Now, I can't remember the names of these things. I can never remember the names. I think one is, I remember Gauss's law. Gauss's law is this one. This one, is this the, no, the Faraday-Maxwell one is the curl of E one, isn't it? I can't remember what the curl of B one is. I'm sure it's got a name, but I don't know the name. Okay, anyway. So that's two of the equations, 2 out of 4, but we've not got the other 2 yet. And I still want to get those. But rather than go through any difficult business, what I'm going to do is I'm going to define a new tensor, or rather technically it's a pseudo tensor. But I'm going to use the word tensor just because I'll get bored if I keep saying pseudo tensor. But I'll explain why it's a pseudo tensor briefly. So I'm going to define a new pseudo tensor that I call the dual Faraday tensor, or the dual field tensor, which is this contraction with this totally antisymmetric Levi-Civita tensor with the original Faraday tensor. So this thing here is often called the dual tensor. And in terms of components, what this does, we know what F mu nu looks like. Just throw in a Christoffel symbol and you're good. Yeah, we wanted to turn this all up into covariant derivatives. That would be fairly straightforward to do that, but we won't do that right now. We remember that this Faraday tensor has got zeros along the diagonal, then it's got components EX, EY, EZ up here, and it's got the B field stuff, down here as well. Or maybe, I can't remember which way around it is again. Where did we write it? The BZ maybe is swapped, but it doesn't matter. So we know what this F mu nu looks like as a matrix. Now, if you multiply it by this tensor here, this Levi-Civita tensor, which is defined in such a way that it equals +1 when you have a cyclic arrangement of 0, 1, 2, and 3. So 0, 1, 2, and 3. If this was 0, this was 1, this was 2, this was 3, this tensor would be +1. And if it's any cyclic permutation of those numbers, so for example, 3, 0, 1, 2, or 1, 2, 3, 0, then it will also be +1. But if you have any swaps of either one of them, so say you had 0, 2, 1, 3, then it's -1, and so on and so forth. It behaves in this way. And if you have any repeated indices, so if you have something like 0, 0, 1, 3, then it's always 0 if you have repeated numbers in the indices. Oh, the Maxwell-Faraday equation for the curl of E. Ampere's... Oh, of course, it's Ampere's law. Oh, yeah, right. Yeah. Yeah, no, I totally forget all these names. Thank you for looking that up, though. Okay. The point is, though, if I plug in this particular matrix form I have of F mu nu, and I multiply it by this form here, what it actually does is it just swaps any B vector, or component of any B vector, with the corresponding component of the minus E over C vector. Okay, so I can write it down. I mean, it'll just take a minute. So what this tensor looks like is it's got a 0, like a minus bx. No, hang on. Wait, what was there on this one again? I've forgotten. This one, no, this one was plus, so it'll have a minus. Wait, will it have a minus or yeah. Minus bx, minus py, minus bz. And then the anti-symmetric corresponding parts. 0. What was that again in that second row? That was a bz. So now that'll be minus ez over c, ey over c, minus ex over c. Mu equals nu according to your handwriting, at least. Yeah, my mu's and nu's are pretty similar. Well, this is like I've got a tiddle on top of the f, a mu and a nu, which all look pretty much like the same symbol. So yeah, I do have trouble with those indices. And so on. Anyway, the point is you just swap b with minus c. Sorry, b with minus e. Okay. But there's something interesting about Maxwell's equations in general, and that is that you'll notice that if you swap E and B in Maxwell's equations, they seem to give you something similar, but except for these source terms. So for example, if you swap B with minus E in this equation, you basically just get back up to this equation other than this annoying source term. Okay? Do you see what I mean? So it's like you've got a curl of E is proportional to minus B. Here you've got curl of B is proportional to minus E. But what I'm saying is if you swap B out for minus E and swap minus E out for B, you basically get this same equation up here. There's a kind of natural sort of duality to them if you swap E and B. And from this tensor here, that is just swapped with a minus sign, the E and B's, you can kind of, in a very hand-wavy, cheaty way, argue that your other two Maxwell equations, so the 2 and the 3 Maxwell equations, that is the 2, 1, is this the magnetic equals electric plus motion? Yeah, exactly. This is how electric and magnetic fields transform into one another. Now we kind of stated earlier that you could combine the electric and the magnetic potential into a 4 potential, and that then this 4 potential will transform as a 4 vector in a covariant way. We didn't prove it. So you can, by thinking about currents and thinking about Lorentz transformations of velocities and things, you can work out a Lorentz transformation between electric and magnetic fields. And then you can, that's sort of your physics side of things. That's where the physics comes from. And then you can show that if you define a 4 potential A mu in this way such that it has the electric potential as a 0 component and the vector potential as the 1, 2, and 3 components, that the field equations it gives you will correspond to the correct Lorentz transformations of the E and B fields that you found earlier from your physics. But we didn't do that. We just I just stated this 4 potential and said, this is a 4 vector. Trust me, if you want to change your scalar potential, if you do a Lorentz transformation on your system which has some electric fields, some magnetic fields in it, the way that these fields mix up and change into one another is just as if you do a Lorentz transformation, or rather the way the potentials change into one another is if you just do a Lorentz transformation on this 4 potential. Okay, if you wanted to find how the fields actually transform, not just the potentials, what you would do is you would do a Lorentz transformation on the field tensor, which is, because it's a rank 2 tensor, you'll need two Lorentz transformations, contracted in with it. But then this will change your E fields and swap your E fields and B fields around and mix things up a little bit, and you'll get these same transformation equations you could find by considering things like, velocity boosts of current densities, turning them into charge densities and stuff like that. Okay, but we didn't actually do that explicitly. So the point is, from this kind of apparent duality, that these equations are very similar when you swap B and minus C, I'm going to argue that the other two Maxwell equations I can write in this way, where this tensor, remember, is the same as the original field tensor we had, but with B swapped out for minus E, and so on. But because the source terms were getting in the way, these things were the same up to the source terms. Now there's no source term on the right-hand side. Okay, and it turns out that this is actually correct, but I've gone out of my way to argue it a hand-wavy way just because I don't want to explicitly try and show again that these equations do come out the same. But you can do it. You would just have to swap some E's and B's around and do things a little differently, but it'll look very similar. So this is this second way of writing the other two Maxwell equations, and as a reminder, 2 is the one about the divergence of B, specifically the divergence of B being 0, and 3 is this one about the curl of E, I think. Yeah, curl of E. This is the induction law, the one that tells you how changing magnetic fields produce currents, that gives you all power generation and things like that, the principle that works on. But what you can do is you can substitute the form of this dual tensor we have in terms of the field tensor, like this, and you can show that this gives you actually an equivalent way of writing the equations that looks like this. Okay. And this is actually sometimes called, or it's a particular class of identity called a Bianchi identity. The same sort of form of the Bianchi identities you get in general relativity. And I think actually it's a more general thing in physics. So I use this word duality, and I used it quite lightly because I just sort of mentioned it looks like these things when you swap them about look similar. But I mean, dualities are a really important principle in physics anyway. And I think it's a general thing that if you have a duality, one of your field equations will actually turn into a Bianchi type identity. I think that's something general you can say, but I can't remember how you prove that, or I can't think how you prove that, and I can't even remember where I've picked that up from by osmosis somewhere. But anyway, this is an equivalent way you can write this equation up here. Okay. And I kind of prefer this way. I think it looks a bit nicer in this Bianchi kind of form. Okay. So yeah, that's sort of a lightning quick way to sort of motivate, with lots of proofs and lots of important steps skipped, how you can motivate this covariant formulation of Maxwell's equations in terms of this Faraday tensor. And you know, it is really interesting. It's sort of, you expect from relativity right away that you should be able to write electromagnetism in a covariant way, because of course it's electromagnetism that really gives you special relativity in the first place. The fact that Maxwell's equations predict a speed of light that depends on these constants related to the vacuum, epsilon naught and mu naught. It took Einstein to suggest this principle of special relativity, that all physical laws, not only Newtonian mechanics, all physical laws should be indistinguishable and the same in inertial reference frames. So between inertial reference frames, there should be no preferred frame, and the physics should always look the same. And this comes from electromagnetism. So it's very satisfying, and we would expect it. Electromagnetism has an equally nice way of writing that electromagnetism has an equally nice way of being expressed in terms of relativity in the slightly more sophisticated 4-vector, 4-tensor methods. Okay. Oh, good. I'm glad that made it a little bit better. Have I ever taken a Mensa test? No, I have not. I mean, IQ is a bit of a... It's a very poor metric. I'm not at all interested in what my IQ is. I mean, also, it's probably just not very high. So I'm not interested in finding out. I think if you find out it's high, what does it do? It makes you a bit stuck up. If you find out it's low, it probably makes you a bit depressed. So why would anyone even bother trying? So no, I've no idea. Well, I mean, so yeah, I'm free to take any other physicsy questions anyone's got. But I was also hoping we could browse some memes on r/physicsmemes for a little bit. So I was thinking maybe I would turn and look through some memes now and have a chat about the physics in them. And then if anyone's got any questions that require the board, obviously I'll just put the board right back up. So let me just change to my screen. Okay. Okay, nice. My audio didn't die. Awesome. Right, you can see my screen now, I gather. Okay, great. So this is just the first in the... this is the hot section of r/physicsmemes. I mean, yeah, let's stay in the hot section. Some of them are probably pretty terrible. Yeah, meme review. Exactly. Infinities in quantum field theory, you can't defeat me. Physicists, I know, but he can. Renormalization. That's a good one. Yeah, renormalization is, you know, a really important technique in quantum field theory that gets rid of these seemingly nasty infinities that you might think make your theory sick. You know, if you get answers to problems, things that you can measure that turn out to be infinity, you might think that's a very bad thing, and that's a flaw in the predictivity of your theory. But actually, these infinities are things you can get rid of. And the way you get rid of them is not particularly mysterious. It's just sort of, you define the variables in your theory that appear in your mathematical equations in terms of things you would actually measure, rather than these sort of bare quantities that are not necessarily measurable, that are just things that appear in the equations. Is that a reference from a QFT book or something? I'm not sure. People, yeah, I mean, renormalization is a bit crazy as a topic. A lot of people really didn't like it, I think, when QFT was, you know, in its heyday. I think, like, Dirac, especially, was very outspoken against renormalization. Oh, right, I see. Oh. Yeah, Dirac was not a fan of renormalization, and I can understand why. It does seem a little funny. I've heard he can solve integrals of functions involving multiple exponentials and logarithmic parameters without Wolfram alpha. Yeah, that is definitely not me. No way. Popular science fans be like, Copenhagen interpretation, many worlds interpretation. Yeah, that's pretty accurate. I personally like the Copenhagen interpretation. I don't know about many worlds. I mean, ultimately, all of these interpretations of quantum mechanics at the moment are totally equivalent. There's no way you can really say any one is more physical than the other. So it's a choice. It's one of these rare occasions in physics where you can kind of make a philosophical choice that is not bound by experiment or bound by poor mathematics and stuff. You can do what you like. You either love physics or you don't understand it. I hate physics. This post was made by teens who failed their physics exam because they didn't study. Yeah, I mean, physics is hard, that is for sure. Oh, nice. Star Wars crossover. Physicists who thought everything had already been discovered. Have mercy, please. Einstein and Schrödinger. There is no mercy. Yeah, I mean, prior to like the early 1900s with quantum mechanics, people pretty much thought physics was done. Then there wasn't much more to do. The rest was just kind of tying up loose ends and finding nice ways of, solving certain differential equations and things to more accuracy and whatnot, but nothing real big conceptual. I mean, not everyone thought that. Quite a few people like that. Quite a few people, I think, did. You find it odd that the Copenhagen interpretation is the most taught interpretation, even though among physicists it's not the most popular by a long way. What would you say the most popular is? Because my experience has always been that the Copenhagen interpretation is generally the one people, I think, quite like. I mean, many worlds is certainly also very popular. I mean, there are a few slightly less mainstream interpretations, I guess. To be honest, I don't know a lot about these different interpretations of quantum mechanics. I really only know the main, the mainstream interpretations. I just know that there's not a lot you can get out in terms of physicsy things by well, you can't really get anything out physics-wise from distinguishing these interpretations, or at least anything you can get out that would distinguish them is very, very speculative. Things about multiverses and so on. I don't know. I mean, in some ways the many worlds interpretation is quite natural, I suppose. But I don't know, the Copenhagen interpretation to me seems like the one with the fewest assumptions, as a kind of Occam's razor decision. I think the Copenhagen interpretation, which I sort of, in my head, I think of as just, it is what it is, is the one I like. Kids on this, I like this one earlier, I forgot I saw this. Kids on this sub when they realise approximations are everywhere in physics. Yeah, that's very true. I think that's always a bit of a startling realisation for people when they first start doing physics at maybe like a university level, or maybe not even then, maybe even later than undergrad level, that actually most problems are not exactly solvable. Pretty much we can solve simple harmonic motion, and that's about it. We can't do much more than that in terms of analytic solutions. But luckily, most things are pretty much simple harmonic motion. Most potentials appear to be, if you expand close enough around them, they look like an x squared or a phi squared potential. It's because of Heisenberg. It's all his fault. Oh, what, you mean the interpretation stuff? Yeah. When engineers act like they're cooler because they know MATLAB, MATLAB is just Python with NumPy and matplotlib. Yeah, that's pretty accurate. The syntax is all pretty similar. To be fair, I know MATLAB better than I know Python. I should know Python better. I always feel a little embarrassed when I tell people I use MATLAB for most things rather than Python. I don't know why, it just feels like it's kind of, I don't know, it feels like it's a bit more of a newbie language. I mean, I don't think it is, but Python to me it always seems more, people use it that aren't just doing physics stuff. It's more used by general computing people and hobbyists and whatever. So it seems like a bit more of a serious language to me than MATLAB. Is MATLAB patented? What do you mean patented? I mean, you have to buy a license to get it. You can't just use, Python you don't have to pay for. MATLAB you do have to pay for. You need a license to use it. I think luckily most universities will buy licenses for their students though. So I've never had to buy a license, luckily. Addicts before and after. Alcohol, weed, cocaine, physics. Nice. Yeah, is that... Which physicist is that again? Is that Heisenberg? I can't remember if that picture is Heisenberg or not. You usually see him with his funny little glasses. And he's got funny little glasses there. I think it looks like him. I'm not entirely sure. You can only pick one. What? One is the Einstein equations. What is that? Is that the standard model? Written out in full in component form? I can't actually tell it. I mean, it looks like it. Yeah, it looks like this, the full standard model Lagrangian. I mean, you can write the standard model Lagrangian in a lot nicer way than that, though. But, yeah, that is pretty chonky. Bay, come over. I can't. We are linearly independent. My parents aren't home. Me. Nice. Fair enough. Correct, those are not linearly independent vectors. So I was chilling at home playing EVE Online when suddenly Fermion... I know, it's gone again. Okay. I mean... So this is about creation and annihilation operators, but surely the AN plus should be there and then it puts the hat on him. And then the AN acts there and takes the hat off him. I don't know. I mean, I get the meme. The meme's funny. It's a guy with a kind of interesting expression. Is his face photoshopped? That looks like it's the same face in all three pictures, just photoshopped onto a guy's head. It's a hat joke, yeah, I believe so. But I would have thought the creation operator should be there that puts the hat on him, and then the annihilation operator should be there which takes the hat off. But whatever, it's a meme. It's not too serious. Oh, we saw this one last week. That's a repost. I fear no man, but that thing, it scares me. Yeah, can't get things heavier than iron made in the sun. It's right at the peak of that binding energy curve. You got an F grade, you're an engineering student, you know F equals MA, let M equal 1, you got an A. Nice. No, the use of a capital A for acceleration is a little bit off-putting. That sounds like the kind of thing a physicist, an engineer would do, though. Made an electromagnetism... Oh, this is some guy posting a... I won't look at that right now. Again, 1 hour ago. Someone keeps posting this same meme. Dwayne Dirac Johnson. Nice. That's good. Almost like using J for current. Yeah, exactly. Or even worse, J for the square root of -1. That is a big engineering move. Ugh. Assume cow of dimension X and Y. That is a good looking 2D cow. Nice. Oh yeah, you meant J for complex unit. You were learning about the effective potential for the case of a photon, and the potential was maximum at 3m radius photon sphere, but is unstable point. Can we make it less unstable, like some plateau around 3m region, to just make a thicker photon sphere? So do you mean like, however you find this effective potential in general relativity? It has a stationary point that is an unstable maxima at some radius outside of the usual circular, or is it in? Yeah, it's outside of the usual circular orbit radius. I don't know how you would make it. Oh, well, actually, for photons, I think there is no stable. Is there? Wait, is there a stable circular orbit for photons in GR, in the effective potential? Well, you've got the line element is 0, so you don't get any. No, I don't. I can't remember. I can't remember now if there's if there's a stable minima or not. There's definitely, as you say, this unstable maxima at 3m, or well, if you say it's at 3m, I trust you. It's at 3m. I don't know. But I don't know what you mean by could you make it less unstable with some plateau? Like, as in, how would you go about making it less stable? I mean, you know, there are probably some metrics of some weird distributions, some weird spacetimes that do have stable. Well, I'm sure there are. There are stable orbits for photons in some spacetimes, but I think in Schwarzschild spacetime, the only parameter really you have is the mass of the object. You know, the mass of your spherical mass distribution that the thing is orbiting. And I don't think there's any way you can tune that to make it particularly plateau. I mean, what you could always do is you could find, if you wanted to try this, you would compute the second derivative at the maxima and then do 1 over it. And that kind of gives you, the curvature, the rate, not curvature as in space-timey curvature, but curvature as in of like a 1D function v of r. If you compute the second derivative at this point r equals 3m, and then you do 1 over it, that gives you the radius of curvature of your maxima of this point on the curve. And you could see what would you have to change in order to make the radius of curvature larger, because the larger you make the radius of curvature, the flatter, or locally flatter, your curve looks about the maxima. But I would expect perhaps maybe it doesn't depend on things like, maybe it would depend on the mass, but I'm not entirely sure. I don't think there's much you could do to change it, really. I think the shape is pretty much set just by the mass of the thing you're orbiting. But there will certainly be spacetimes for which you could have a stable photon orbit. Does a moving black hole have symmetric photon spheres? Well, so if you take the metric, centered on the black hole, if the black hole is actually, no, I'm not sure. I think you can't quite just you can't apply like a argument about inertial reference frames. So you couldn't say, well, the black hole in the reference frame of the black hole, it just has a normal Schwarzschild metric, and then you can transform to the outside, because actually your transformations to switch into that reference frame will be non-trivial, and neither reference frame is inertial, so you couldn't just boost into it. So I would expect that in the reference frame of the black hole, in whatever reference frame would measure the black hole as stationary, it would just have an ordinary Schwarzschild metric, but then swapping out into the, to the observer that would see the black hole moving, I think that would be probably quite a non-trivial transformation to do. I'm not sure how you would do that. Yeah. No, I'm not entirely sure. I mean, I am certainly, from the perspective of somebody outside of somebody for whom it appears that the black hole is moving, that would not have a spherically symmetric metric, which I think is what you mean by photon spheres, right? But from the perspective of the person, someone moving alongside the black hole, for example, I expect it would do. Well, in fact, I'm sure it would do, yeah, because there's no such thing as a specific inertial reference frame. So from the perspective of somebody who measures the black hole to be stationary, they would see it the same normal Schwarzschild setup you'd expect ever, because of course there's no perfect inertial reference frame where a black hole is still, and if it's moving with some velocity with respect to that, it's not still. There's no such thing as this special inertial reference frame. But as for how you would actually find the metric, for somebody that would observe the black hole to be moving with some speed, that would, I think, be quite a non-trivial coordinate transformation. I'm not sure how you would go about thinking about that right away. Probably you could like write down the coordinates of a person. No, actually, no, never mind. Yeah, I'm not sure. I'd have to think about that. I don't think that was your question anyway, though. But that's another question I'd have to think about. Society of root a plus b is equal to root a plus root b. Yeah, pretty much. I mean, same thing as like a plus b all squared is equal to a squared plus b squared. That would be nice. That would have made, 16-year-old maths classes a lot more pleasant for me. Those who climb mountains have great potential. I don't know who that quote is from, but yeah, I mean, it could very well be from U equals mg. Though I guess depending how high the mountain is, maybe that becomes less of a good approximation. You might need to think about Newton's equation for it. Oh, that's okay, no problem. Light rays will never meet, light rays will meet at infinity. Yeah. That's assuming you have some kind of geometry that wraps around like that. Like how the complex plane has a single point at infinity. So all lines, even non-parallel ones that go to infinity in the complex plane on like a Riemann sphere will meet one another at infinity. When you count in milliseconds, just went from 0 to 100 real quick. I mean, yeah. Physics teacher when you don't write the unit behind your answer. I mean, units are important. I think that's also, this guy kind of just looks like maybe what I would look like if I really let myself go. He's got the bow tie, he's got the glasses. That's not what I aspire to be, the lawyer from B-movie. Hopefully not. Schrodinger's douchebag. One who makes douchebag statements, particularly sexist, racist, or otherwise bigoted ones, then decides they are just joking or dead serious based on whether people in the group approve or not. Yeah, that is, seems like a fair statement. Not a very nice thing to do. Friction and air resistance in high school. I still don't think I ever take air resistance, or have ever really taken air resistance into account unless explicitly told to. It's never that important. I mean, except when it is. I can't be bothered to watch this, it probably has sound. Mars atmosphere density at surface, 35 kilometers. Huh. Something seems a little wrong about those units to me. Isaac Newton. Bonk. Nice. I feel like we saw another one like that last week, but instead had the inverse square law, instead of just the value of little g. This post was made by the Drift Velocity Electrons gang. Having done some research, I misinterpreted the popularity of the Copenhagen. In a poll done at the Conference of Foundation 2013, Copenhagen was favoured by 42% of attendees. Oh, okay. So what were the others then? Was 42% the largest percentage? Or did one of them get more than that and one of them get, a really tiny one? Was Copenhagen the most preferred in that poll you were looking at? Assume those cows are spherical. Some smart farmer inventing numbers to count cows. That's funny. Yeah. I mean, I guess all numbers came from wanting to just count things to know how many you had of something, not thinking about these more difficult physics problems of hundreds of years in the future. Any complicated coupling problem. Assume FO is much, much greater than 1 and BI. I don't know what FO and BI are there. Lumped capacitance model. Oh, cooling problem. I thought it said coupling problem. Yeah, I'm not sure what these specific terms mean, actually. Oh, it was the largest by a long way. The information base 24%, Everett 18%, objective collapse 9%. Oh, nice. Thanks for the link. That's interesting. I mean, is this paper just reporting the one result, or... Oh, yeah, there we go. Oh, it was Max Tegmark that polled the people. Huh. Nice. That's always good to know. When you discover gravity but can't attract anyone. Yeah, I mean, I'm pretty sure it's... I don't know where this history comes from, and it feels a little mean to perpetuate the history, but it's a thing I always hear that apparently Newton never got on very well with ladies or men or basically any other humans. But I mean, imagine if it's not true, and like for your entire history, you do all this great stuff, but there's always a kind of caveat buried deep under your name that you died like a virgin or something. That's a pretty rubbish thing. So I mean, if it's not true, that's pretty sucky for Newton. But it's probably true, to be honest. I think he was a pretty horrible guy overall. This man has solved it. Dark matter is just matter with wall and invisibility hacks. This rumor is brought to you by the Leibniz gang. Yeah, I mean, I guess it's a fair compromise, you know. If you believe that Newton stole calculus from Leibniz, why not start a rumor that Newton never got laid? Seems fair. When my mum walked in, I immediately switched to porn because this was easier to explain. Nice. Oh, that's Brian Green. Sweet. The YouTuber explaining black hole, me watching the video for the 67th time. Okay, let's see. Black holes do be hard. Assassin's Creed logo in dispersion curve. Oh, this brings back horrible memories of condensed matter physics. Ugh. God, I don't even want to look at that meme. I love this meme format with the dog and the bonk. It just makes me laugh. Celsius, Kelvin, Fahrenheit. Wait, what? Surely it should be the other way around. Surely Kelvin should be the one bonking Celsius and Fahrenheit. Who uses Fahrenheit? Well, actually, I mean, to be fair, people use Fahrenheit in America, I guess. Kilogram of steel, 1 kilogram of feathers. American gang. Yeah, exactly. What if I gave 1 in 10 and 20 electrons to you and created the force of attraction the size of a bus? Just kidding, unless 1 in 20 electrons. Why do you think animals are inferior? Can they solve integrals and derivatives? Can you? Fair enough. Opaque object, light. Light, translucent object. Nice. Poor cat. Fair enough. That is a pretty ancient meme format. That Ron Burgundy one. I haven't seen that in quite a while. I think I saw this one last week. A lot of these, like, even though this is only from 3 days ago, I swear like I saw this same meme last week when we were looking through some. But yeah, again, units important. Degree in theoretical physics, theoretical degree in physics. Covariant easy to find the difference between this picture and this picture. If you have a theoretical degree in physics, that does mean you have no degree in physics. My degree is purely theoretical, it doesn't exist. Quantum entanglement be like. I don't get the background. Is that Mars, and is that, I mean, some of these memes are just crazy. I don't even know. I like the principle of this meme though. You remember in your intro E&M class, your professor went on a rant why the Coulomb is a stupid unit, because if you put two 1 Coulomb charges 1 meter apart, the force between them is roughly equal to the weight of the entire country of Sweden. Yeah, it's a pretty stupid unit. I mean, it's, in a way, it's not as bad as, you know, the amp, which, I mean, is, you know, is a stupidly large unit because of the fact that a Coulomb is stupidly large. But also has the wrong direction. The fact that electron current is in the opposite direction to conventional current is something that has always annoyed me, and I think whenever I'm like teaching circuit stuff, people always get annoyed about that, because you end up slipping up talking about, oh, well, the current flows from one capacitor plate to the other, and it deposits positive charge from, moves positive charge from one, moves positive charge to the other. And then they're like, wait, but what's the positive thing moving? Why, like, what are these positive particles? And then you remember, oh wait, I should have explained that when we talk about conventional current, you kind of just have to imagine, you know, you explained it explain the physics in terms of electron current, but then when you convert to actually how you solve things and how these things are written, you have to go back to conventional current, which is about positive charges, which don't actually, you know, exist. There are no positive charges moving in a current. This reminds you that there are unit algebras, because, like, you can't add different units, only multiply. Yeah. Yeah, that's true. You can't add different physical quantities together that represent measure different things. It's kind of a law, I suppose, that comes from observable things. You can't measure something. It's like using two different pieces of apparatus in one go. I don't know. It's just I know what you mean. Yeah, when you don't have enough energy. Photon. Oh, is that a photoelectric effect joke? Nice. Don't tell the astronomers. Oh yeah, they have some really funky units they put together. Any science, you think you're better than... I'm better than you. I mean, it's not false. One of their units is log meters, but they won't admit it. Oh, right, yeah. Yeah, you can't, because you can't put anything with a unit into a logarithm or an exponential. I guess, I don't know. They just ignore the unit, I suppose. They scale it against a unit scale that just happens to be 1 meter, and therefore they don't write it down, which is kind of cheating. But, whatever works for them. Also, yeah, no, I agree, not false. I was rewatching an old Tom and Jerry movie when I noticed this scene. Is 1U an actual unit? I see that they're using 1 AMU equals 1.66. Oh, yeah. Oh, the guy the professor in this thing just likes the fact that an atomic mass unit is given by that. Dislikes 1U, and then I can't even read that number. Huh. Anyway. You're recently done learning all the coordinate systems for a project. I've had it up to here with astronomers. I feel you. Teachers who make physics boring are criminals. My physics teacher. I'm going to pretend I didn't see that. Aw, that's mean. I had lots of really good physics teachers. I mean, well, I suppose that would make sense because now I like physics a lot. A lot of people that don't have good physics teachers don't like physics, which is a real shame. Thanks, Wolf from Alpha, really cool. Yes. The 3.148 foot per second is... Oh yeah, the slug. This is like a non-SI unit for mass. Like if a pound is what you measure force with, the slug is the non-SI mass unit, the imperial mass unit. I don't even know what a slug is like in terms of how many kilograms it is. It's a really weird unit. Ray optics gang in the 1920s, wave optics gang in the 1920s, quantum mechanics gang. Fair enough. What's your sign? I'm a Leo. I don't believe in that made-up nonsense. So true. Oof. That hurts. If all the people in the world stood on a chair and jumped off at exactly the same time, they could knock Earth out of orbit. That doesn't seem too true to me. I mean, it's definitely not true. I do like some of these pages. I love reading through some of these like Facebook groups that people make where they talk about physics, but like none of them are physicists. So they will just kind of come up with their own theories that involve literally no maths and like no even reading. They're just like, oh, I think that the universe is made out of dark matter times 8, and the speed of light is just because time speeds up every time you look at it, and you reread it and it makes literally no sense. And all these people, they think they've solved physics, and like they send... I'm pretty sure in one of my lectures last year, like in one of my quantum field theory lectures, I'm pretty sure there was a dude that was a bit like that. There was this kind of older dude sat at the back that used to watch some of the lectures, and I think in like the last lecture, he like came down and he presented the lecture that was... Oh yeah. Is it Snarchive? I can't remember, is that what the website's called? There is this one, isn't there, that is all... It's like an... there's no moderation on it, so people can just upload absolutely anything. I was thinking about like doing a stream just going through that and trying to deconstruct some of these crazy theories, but then I forgot what the name was. It was Snarchive. Oh, okay. But yeah, this dude that used to sit in our AQFT lectures, I think he then, like, in the last lecture went down and presented the lecturer with like a book of his own writing that he probably thought solved all of physics. But I don't know. I somewhat doubt it does. Oh, there we go. Yeah. Oh wait, no, this isn't the one I was thinking of. There was a no, there was a different one that wasn't Snarchive. I can't remember what it was called though. There was this guy in one of my quantum classes who insisted Schrodinger's equation couldn't be linear because it had a second derivative. What do you mean? As in, like, the solutions couldn't be linear? He was like confused. Oh, I see. He was confused about linear versus first order. Oh, yikes. I mean, fair enough if you have that misunderstanding, but it's like, I don't know. Some people, when they get a misunderstanding, it's very hard to tell them that they're wrong, and they'll just kind of follow through with it and assume everyone else has got it wrong. Fermi betting the atomic bomb will ignite the atmosphere and wipe out humanity. Oppenheimer betting it won't even work. Teller putting on extra sun cream. Oh, I see. Yeah, that's a kind of weird little misconception. Oh dear. Extra sun cream. Yeah. I mean, so many of those people that worked on the Manhattan Project, I think they did get pretty, a lot of them I think had cancers and stuff and pretty horrible health things. So the sun cream probably didn't do too well. I don't know how Teller died, actually. I'm not sure what killed him. Time is absolute, Isaac Newton. Only a Sith deals in absolutes. I will prove time is relative. You will try. Nice. Prequels physics crossover. Excellent. There's a game archive versus Snarchive where you have to pick between one title of an archive article and an AI generated one. Oh yeah, someone sent me like a piece of code they'd written or something which randomly generates paper titles based on certain seed things. I guess that's the same thing, like an AI generated thingy, paper title. Whoa, I've just realized the time. It's like 9 o'clock. I actually have to go and eat dinner. Wow, I totally lost track of time. So yeah, I guess I will leave it there for now. If anybody wants to, feel free to join my Discord channel if you like. And then yeah, I will see some of you on, what day is it today? Today's Tuesday. I'll see some of you on, wait, is it tomorrow? What day is usually, what day do I usually do Mario Kart? Thursday, right? Yeah, Thursday. Yes, Thursday. I'll see some of you on Thursday for some Mario Kart and more physics chat. And then, and then I need to decide what to do on Saturday for the spacewalky stuff. I'm not sure. If anyone has any suggestions, feel free to pop them in the Discord about spacey stuff we could talk about on Saturday. Maybe more black hole stuff. Maybe, who knows? Whatever. Okay, great. No problem. Thanks for coming along. So yeah, I'll see some of you guys on Thursday. Okay. Bye, everyone. Bye.